Hi everyone, this is our first video of single variable calculus, and in this video we'll be learning about Rolle's theorem and its geometrical interpretation. Before starting this, you should have a basic idea of what a limit, continuity, differentiability and some few important and most used differentiation formulas, and those things were already provided in my previous video, and you can find those link in my description. And now coming to this Rolle's theorem, before starting about what's the Rolle theorem actually is, you should know why should we learn this Rolle's theorem and what way it is used. See, firstly, this Rolle's theorem, it is used to understand the behavior of a function. Okay, to understand how does a function behaves. That is the main reason why we study Rolle's theorem, and I will be giving you one real life example. And before that, it also acts as a foundational block for deeper analysis in calculus. As we proceed further, we may find this use again. Helps in real world like predicting maximum heights or like turning points in functions which represents like a physical phenomena. With a example which I am going to give now, you will get clarity about why do we use this Rolle's theorem and what way it is useful for us in our daily life situation. Let us suppose, like nowadays we may hear that if you were traveling in a vehicle and your speed limit exceeds, like for example, let us suppose this is a road. Okay, this is a straight road, and let us suppose that if you are traveling at a speed of greater than 60 km per hour, then you will be charged. Okay, so for that, nowadays we may see that there was some like sensors or CC cameras placed. For example, let us suppose that you are moving on a road in a vehicle, and let us suppose this is your point A and this is your point B, and let us suppose that a CC camera is placed, a CCTV is placed at the point A, and it is also placed at point B. Now the condition is, if you are moving in a speed which is greater than 60 km per hour, then you will be fine. Okay, you will be fined. Okay, now when see here, you are moving at a high speed, and whenever you reach this point, you are coming like in a very slow way, like you are decreasing your speed, and you might think that at this instant I have reduced my speed, so I may not get charged. But again, the moment when you left this point, that means when you are not under the surveillance of CCTV, you will again increase your speed, and then when you are coming near to the CCTV, again you will decrease your speed, and then you will move with a greater speed, and you think that though I may like crossed 60 km per hour, no one may recognize me. But the actual point is that how do they identify that you have crossed is, we know that speed is equal to distance by time, right? They will record like at this point A, for example, you have started your journey, and at the point where you reach A, it is like 2 minutes, and uh, you have reached at the 6th minute to the point B, and they know the distance between this A and B. We know that speed is equal to distance by time. Okay, then if let us suppose the distance to be L, and the speed is also known. Now, by using this Rolle's theorem, they will calculate this speed between these both points. For such situations, Rolle's theorem is used in our daily life. Okay, and that is the reason why we should learn this Rolle's theorem. By now, hope you are clear with this. And now coming to our actual topic, that is the statement of the Rolle's theorem. And after this, we are going to learn about geometrical interpretation, and by that you will get to know the meaning of this statement. Firstly, if a function f of x is defined in the interval a comma b such that, it is like, here we are considering a function and that function is named as f of x. Okay, if a function f of x is defined in the interval, that is closed interval a comma b, such that the first condition is your f of x is continuous in closed interval a comma b, closed interval a comma b. And the second point is f of x is differentiable in open interval a comma b, open interval of a comma b. And then the third condition is your f of a is equal to f of b. Then if and only if these three conditions are getting satisfied, then there exists at least one point c in open interval a comma b. That is, it is in between this a and b, right? That means a is less than, c is less than b, such that your f dash of c is equal to 0. You will get to know about this, what it is actually in the geometrical interpretation. Okay, but now if a function f of x is defined in the interval a comma b such that uh, these three conditions to be satisfied, that is f of x is continuous in closed interval of a comma b, it is differentiable in open interval of a comma b, and f of a is equal to f of b. If and only if these three conditions get satisfied, then only you have to check for this, that is, then there exists at least one point c in a comma b, that is a less than, c less than b, such that your f dash of c is equal to 0. Now coming to this geometrical interpretation. As you can see, this graph, it is a function y is equal to f of x. Okay, there are no breaks or gaps in between a and b for the given curve and including at the endpoints. Hence, the function is continuous in closed interval a comma b. What this actually mean is, see, here this is your x-axis and this is your y-axis and this is your function, that is f of x. Okay, and let us suppose a and b to be the endpoints. Okay, this is a and b or the endpoints of this function, and let us suppose this as a point p and this as a point q. Now we know that, so if we suppose that y is equal to f of x, a is the function, then this is nothing but at this point a, that is x is equal to a, that means y is equal to f of a, that means this height is nothing but your f of a. And similarly at this point b, y is equal to f of b, that means this height is equal to f of b. Now at this point it is f of b into f of a. See, this function is continuous whenever there are no breaks or gaps in this function, then we say that function is continuous. Since there are no breaks or gaps in between a and b, see, wherever you may see in between a and b, it is clearly continuous. There are no breaks or gaps in between that. So, and also at this endpoints also there is no gap, right? Since there is no break or gap in between this a and b for the given curve and including at the endpoints, hence the function is continuous in closed interval a comma b. Hope you are clear with this first point. Now going to the second point. Since a unique tangent can be drawn at each and every point in the interval except at the end point, the function is differentiable in open interval a comma b. What does this actually mean is, you will be knowing about this in the next few seconds. And now see, at whatever point you may see in between a and b, you can draw a unique tangent, but at the endpoints you cannot draw. I'll explain the reason for it. And now coming to this third point, at the endpoints a and b, they are at the same height from the x-axis. This is what we have seen. So if we consider that a function is y is equal to f of x at the point a, since your x is equal to a, y is equal to f of a, and y is equal to f of b, since this both this both are at this same height from the x-axis, we say that f of a is equal to f of b. At the endpoints a and b, they are at the same height from the x-axis. That is why we say that f of x is equal to f of b. This is how these three conditions have arrived. That is, f of x is continuous in closed interval a comma b, f of x is differentiable in open interval a comma b, and f of a is equal to f of b. But here, in order to get more clarity about this second point, see, this is how our graph is, right? And this is our point a and this is our point b. What is differentiation actually? It means like dy by dx. It means like you're just calculating simply slope, right? If you can see, like between 2 points, if you can see here, you can clearly draw a tangent. But if you can see this endpoint, you can't draw tangent in this way, because below this there is no curve, right? So your tangent will be like only half. It means here at this endpoint we are defining only at one side, not at the both sides. But if you can see here, you can define it on both sides. If and only if we define it on the both sides, then only we say it to be differentiable. But in this case, it is only defining for the half part, and another half part is not there here. That means at the endpoints this tangent is not existing. If the tangent is not existing, that means your dy by dx is also not there, which means that it is not differentiable. That is the reason why you are taking open interval of a comma b. Hope now you have got clarity. That is, since a unique tangent can be drawn at each and every point, see, at each and every point you can draw this unique point, except at the end point. So the function is differentiable everywhere in between a and b, but not exactly at the point a and b. And by this we have completed this geometrical interpretation. And this graph is about like see here, at we have chosen that there exists at least one point c in a comma b, right? Here just we are concerned there must be one point, and beyond one point also, like it can consist more than 1 points also. Here in this graph we are taking only 2 points. If there were more than 2 points, so for that the graph is in this way. And now your conclusion: therefore there exists at least one point c in between a and b, such that the tangent is parallel to x-axis. And by this our Rolle's theorem is verified. And this is all about Rolle's theorem and its geometrical representation. Hope you are clear with the concept. And if you have any doubts regarding this topic, feel free to ask me in comment section. And in next video we are going to discuss few problems on this Rolle's theorem. Stay tuned, subscribe my channel for more videos, and thank you for watching.